Hi, everyone. Welcome to our talk today on Bootiful Kubernetes operators. It's our first time doing it as a live stream type of thing, so it'll be a little interesting seeing how this works exactly.
So hi everybody, Timo here, and today we want to talk about beautiful Kubernetes operators. Let's start with a short introduction. So first, Tiffany, please introduce yourself.
Yeah, hi. So I'm Tiffany Jernigan. I am a developer advocate here at VMware. Twitter or X, if you still use it, sometimes I forget that exists since it's a different icon now. I have my handle there, and then there's also LinkedIn and other things if you want to get hold of me elsewhere.
Perfect, thank you. So and I'm Timo Salm. I'm developer experience pre-sales specialist for the EMEA region with a main focus on our internal developer platform product, so Tanzu application platform and Azure Spring Up Enterprise, which we jointly built with Microsoft. And before we have a closer look on how to actually build Kubernetes operators with Spring Boot, let's first have a look why we should actually run our applications on Kubernetes. So what are the benefits of Kubernetes? And actually, Kubernetes has several benefits. And as you maybe know, it's nowadays the infrastructure and abstraction standard for modern infrastructure. The reason for that is that it really enables a hybrid cloud model, so it's available everywhere. It's available on premises, but also on all the major public cloud providers, like for example AWS or also Google Cloud. For software developers, it also brings a lot of capabilities, which makes this platform really interesting for cloud-native applications. And one of those is that actually it really shortens the software development cycle with a fast deployment and provisioning capabilities of these containers. And again, it's really important for modern software development because, as you maybe know, the software development really actually moved from a traditional waterfall approach where a lot of requirements were actually planned before implementing them, and they were then implemented in several months or even years until the first release, which actually built up a lot of risk. And because of that risk, to reduce that, nowadays a lot of the software development moved towards agile, and with agile it's important that you actually release the software as soon as possible and as often as possible to really reduce the risk. And for that, we need those capabilities. Another really important aspect of Kubernetes, or what it brings to the developers compared to traditional software development, is that it gives you a lot of flexibility regarding the applications or the stacks you run your applications on, compared to one or two supported stacks in the past where you had, for example, okay, so here's the WebSphere stack and an Oracle database. And let's now have a closer look what Kubernetes operators actually are, because as you maybe also know, Kubernetes is more a tool to build a platform than a platform. It provides base functionality, but to really actually get value out of it, you have to, in a way, integrate a lot of solutions that are available in a really huge ecosystem. In the best case, build a higher abstraction on top of Kubernetes so that developers can really be productive.
So in like things like robotics or automation, you have a concept of a control loop, which basically is a non-terminating loop. In other words, a loop that just runs forever. And this loop then regulates the state of a system. And basically, you're trying to match whatever the current state is with whatever your desired state is. So if we look at this example here, if we're deciding, hey, I want to set the temperature of my thermostat, that's whatever our desired state is. So this is in Celsius, for instance. So the actual room temperature is the current state. So say if it's 28 degrees and we want to make that we want to bring that down to 24. So basically it's just like working on making the current state closer to our desired state by, in this case, using specific things, maybe like an AC or maybe if it's a different direction of turning on a heater or something like that, which is what I just did in the room in my hotel right now before this. So in Kubernetes, we have controllers, and these are control loops that basically watch the state of your cluster. then they make some sort of like request for changes where you need to have the current state to get closer to whatever that desired state is. And these controllers track at least one of the Kubernetes resource types. And then the Kubernetes control plane has a component that's called the controller manager. And that runs controllers that manage the default Kubernetes resources. So there's things like a controller for your deployment, there's one for your replica sets, etc. And there's other ones that different companies have made, maybe something for some specific database or whatnot, but both maybe the built-in functionality or what someone else has created might not be sufficient for whatever you need. And therefore you may need to like extend these resources or implement your own new ones. So therefore you can like create and run your own custom controllers. So there's this concept of the operator pattern, and it's used for extending Kubernetes with basically a higher level of abstraction. And so it combines two things. So there's the custom resource definition. You might have heard that as just like CRDs, and then also custom controllers. So the CRDs basically let us define like new resource types on the fly to extend Kubernetes basics types. So for instance, you could have like a database operator who defines some sort of like PostgreSQL cluster resource or something. But these CRDs are just merely data structures. They don't actually do anything on their own. So we need some sort of code to back them. And then basically so there's operators, and they basically consist of custom controllers that continuously monitor the state of their custom resources. So when like some sort of custom resource is created, maybe it's updated or deleted, the corresponding controller then takes whatever action it needs to do to reconcile the actual state with whatever your desired state is. So this is basically a diagram of the custom controller that we're going to be creating in this talk. So first off, when you communicate with Kubernetes, everything talks through the API server. And then the API server then saves the request to the control plane database, which typically is etcd. So for instance, we have this thing, you may have seen something on the left with maybe a pod, for instance, or a deployment or something else. So if we want to have this foo resource, this then basically gets added to the database. But unless we have something asking the API server to do something with the resources, nothing actually happens. Like it doesn't know with just that information what to do with a foo. What is a foo? What am I doing with that? I have no idea. So this is basically where we need to have a controller. So basically, in this example that we have, we'll be creating a foo, and a foo will create a deployment, which uses a deployment controller. This then gets added to the database, and then the deployment controller then will inquire the API server and know that there was a request for a new deployment, which then continues down for like a replica set. And like in our specific case, we'll be using the Nginx image. And then we'll also have a config map that basically will alter the web page, because by default with Nginx, it's just like a welcome to Nginx page. And we're going to be using a config map to go and change what is there. Some of the initial code and things that were created for this like a year ago were done by Josh Long, and some things also with Core Ironclad before Timo and I started doing more things with it. And then also there is the scheduler, which is basically another type of controller which assigns nodes for the pods. So it's just a bunch of controllers galore, basically. So we have this environment set up that currently is not out in the world yet. Working on it. But basically all the demo things that we're going to be doing are going through here. So basically, just to like start from the beginning, I was mentioning CRDs. So basically, the CRD API resource allows you to define some sort of custom resources. So this is the CRD that we have for our foo. Like if you're not like diving into things, you may not see this for like pods, etc. But there's things like this exist for how it's defined for the different fields and resources for pods and deployments, etc. But since foos don't exist, we have to go and create our own. So like the name for it has to be some sort of valid DNS subdomain. So ours is, for instance, is foos.spring.io, and then we have like a spec and a group. There's things like what's the kind, which is foo, giving it the option of like what the name is for a plural, for a singular, just like you can do pod or pods, for instance. Then there is this open API v3 schema. And then within that, you can choose like you can create specific things that you are giving a name to. So for instance, nickname here is something that we created. It's just going to be a string that you can fill in, and it will later be using this for the controller and other things that we're going to be creating in the end, which it'll make more sense when we actually start diving into it a bit. Okay, so now we can actually go and create this. You could also use a kubectl apply. A difference is whether you're overwriting something that may or may not exist in advance. So then if we do a kubectl get CRDs on this, we can now see that this was just created. There's also the ability to do an explain. If you haven't explained before, it can tell you what some of the different fields are inside of some sort of object. So here we can see that the field is nickname, and it's just whatever name that you end up putting there. So then after we have this CRD object, now we can actually create a custom resource using this, since the concept of a foo exists. So now I can actually go and create a foo. And then for the name, we can just name it, for instance, my first foo. And then for the nickname here, we're just calling it spring, which again will make a little bit more sense when we actually start creating code and running things. So then we can go and create that as well. So right now we have a foo. There's a thing for it, but again, there is no code that tells it what to do. So this is where the controller comes in. All right, so basically you declare the desired state of your resource, and then this is where we're actually starting to go into code. Since this is Spring Mentor, things are in Java and using Spring. So basically, we're using this code to be able to determine what state do we want things to be in, and that will be used to therefore sync things from our current state to whatever our desired state is. So the best way is to start from start.spring.io or the Spring initializer. So you may have seen this before. It's a lot more helpful than just trying to start completely from a blank project and just start creating things. But so basically, you can choose whether you want to use the default of Gradle Groovy. There's Kotlin, there's Maven, and then you can choose different dependencies that you might want in there, such as whether you want GraalVM native images or Lombok or just a bunch of different things there, and that it will basically create a zip file for you. And you can also explore into this. If on there, you can click explore and see what all is being created beforehand, just to make sure that it's everything that you want to be in your zip file that you end up pulling down. So we already did this, and basically are just going to go and unzip it. So it gets us most of the way through things, but it doesn't have something specific for the official Java client for Kubernetes. So we will need to actually add this to the build file. So we can see in the second line there on line 20 that it's adding the Kubernetes client Java Spring integration.
And yeah, so now we have more or less everything to get started implementing our Kubernetes controller based on the library we have here. And the first thing we actually have to do is we need a representation of our new resource that we created, so the foo, in our Java code to, in a way, interact with it and update it. And for that, there's also a tool available. So in that Java Kubernetes client project, and it's containerized, so you can run it on a Docker runtime, for example. What's actually doing is that it's creating, for example, a kind cluster, so a really small Kubernetes cluster. It's applying your custom resource to it to actually fetch the open API specification from the Kubernetes API. And then it's using the Open API Gen library, the Java library, to generate those Java classes for you. I could also run this here, but at the end, we are currently running this workshop in Kubernetes, and therefore it would be a setup where we run a container in Kubernetes that's actually running a Kubernetes cluster inside just for that functionality. And therefore, in addition to that containerized utility, which you can see some documentation is here. If you just go to the project, so github.com Kubernetes client / Java. Here's all the documentation about that. We will actually use, or what we use is the GitHub action, which is also available here. You can easily set it up in your GitHub repository where you have your controller code, and then based on that, it will generate those classes for you. And that's something based on this documentation we already did here, and we'll also just download them. You can see we have a foo, we have a foo specification, which is the reference from the foo object, and we have a foo list to have actually a list of foos. And if we have a closer look, it really looks like generated code. If you would do that yourself with Open API Gen library, you can specify a lot of stuff, and you can also override some of the environment variables of the container to, for example, choose which library you want to have, for example, for the also JSON mapping, etc. But you can see with that configuration, so out of the box one, it really looks like generated code, but actually it more or less generates everything we need to interact with those or this object in the Kubernetes cluster. As we now have a representation of our resource, it's time to get started actually implementing the functionality of this Kubernetes controller. And as already said, the Kubernetes Java client more or less provides everything we need for that. And the first thing we have to do is configure our controller. And for that, we will just create a configuration here and have to, in a way, provide a bean of type controller. And as you can see, the Java Kubernetes client provides a builder for that to configure the controller in a more fluent way. You can see here we just provide minimal configuration. There are a lot of more options available. So with the default builder method here, we actually use a lot of default configuration. You can see one parameter or of the default builder here is the shared informer factory. And what it is actually, it's a factory that registers all informers that are available. We will learn a little bit more what informers are in a second. Tiffany will talk about that. But actually what an informer is more or less a cache for a specific resource, so that all the controllers that are available for a resource don't have to call the Kubernetes API all the time to fetch the current state. So we are reducing a lot of requests to actually the Kubernetes API with those informers. And so why do we need this shared informer in the builder? Actually, we need it because based on that, it will be checked whether there's an informer available for the resource that we are watching on. So you can see this watch function. We're actually defining here that we want to watch the full resource. And this shared informer factory will check whether there's an informer available for foo. So at the end, whether there's a cache for foo defined. If not, it will fail. We also define the resync period, so how often the current state should be checked against the desired state. And then we configure the reconciler, which is actually really the business logic. So what has to be done to, in a way, get to a desired state. And last but not least, we also define a ready function, which is more or less a method that checks for a specific prerequisite to run the controller. In this case, it checks whether all the informers are synced before running the container. And last but not least, that's only something for the demo here. It defines how many concurrent threads are used for this controller. So yeah, in this case, 2. The default is something around 20. So we're just reducing the threads here for this demo purpose. And yeah, with that, we have our bean of the controller. And what we have to do now is we have to register all our informers and also then run the controller. And we do this actually by just command line runner here. So you can see we use the shared format in factory and the start all registered informers method, and then we run the controller via the run method here. Last but not least, we have to add the imports. So you can see that more or less all the functionality or things we use that were special are part of the Kubernetes client, and then for sure all the default Spring and Spring Boot libraries. And if we would actually build up our application now, we would see that for sure some of the dependencies we have here, like the reconciler, which is actually our business logic, is not available yet. So those beans are missing, but in the next few steps we will implement them or provide implementations for them, and we will start with the informer.
So yeah, just to like reiterate what Timo had just said. So basically at the smallest level, you have the concept of informer. And this is, again, so you don't just keep pulling the API server like constantly, so it ends up caching it instead. Then there is next the shared informer. So basically this can share data across multiple instances of the informer so that you don't need a bunch of different informers for the same type of stuff. And then there is also the concept of a shared index informer. So basically then it makes it so you can actually look up the things by various keys instead of just being like, oh, here's a bunch of them. All right, now what? So basically, we first need to create a generic Kubernetes API for our generated foo class. So it just basically takes in our v1 foo class. We have the v1 foo list, and then we have spring.io and just basically several of the other things that we had looked at before. So yeah, we have spring.io, we have v1 and foos, and then we also take in an API client. All right, so then now we'll basically need to configure the shared index informer. So, I mean, you're already aware of this at least by name, and we talked about it a little bit, but so basically we need to create that. And so that takes in the shared informer factory. And then based on having both of these things now, as with most everything, the way that we have it set up right now, we can't just like auto have it pull in imports. We actually are just having a thing that we're adding in those missing imports by default. If we were to go and run this again, which we aren't doing at the moment, it would basically complain again and say, okay, hey, now you're missing something else. And basically that's where the reconciler is. So basically in this next session is going to be all the things that are actually telling the controller what is actually happening. Since right now, nothing is specific to saying, hey, I want to create a deployment or I want to create a config map or different things like that. Right now, there's no actual logic for what is happening with our controller.
Okay, so then now it's time to create this controller. And for that, the Kubernetes Java client provides an interface that we have to implement. So the interface is just called Reconciler, and it provides it defines one method that has to be implemented, which is called the reconcile method. It has one parameter, a request. What a request provides is actually just the information you need to uniquely identify a resource. So in this case, the name and the namespace. So not actually more information about the resource, the spec, the configuration, etc. Only those two, and then you have to use the cache, so the informer, to actually fetch this additional information you are interested in. As a return type, it has a result. What the result actually defines, you can see it here as a default. It has a false as a parameter. That means that the request was successfully handled, and it doesn't have to be reconciled again. And if it's true, you actually trigger a reconciliation after some time, because the request was not handled successfully. So the same request will try to be handled again. So let's start with the actual implementation of our example. And as you know, what the desired state of a foo is, it specifies a nickname, and what we want to have for a foo is actually a deployment, a web server that shows a website with a specific greeting of such a foo based on the nickname. And for that, we will start first fetching our resource to see how to configure the config map with the contents that will be then displayed by the deployment. And to do that, we are actually using our informer, as mentioned. So we are fetching the resource information from that cache. And for that, we have a lister class that has a parameter, the informer, and a namespace. So it will list all the resources of a specific type, which is defined when we created or initialized this specific informer for the foo resource. And then in the lister, we have the capability to actually fetch based on a name our resource. And yeah, if there is no resource with that name in the namespace that is defined here, then the resource is null, or it can be also be that it's not null, but actually the deletion timestamp is set, which means that yeah, the resource will be deleted, and therefore we also don't have to handle this request anymore. So this is then yeah, that we directly say, okay, it's successfully handled, because actually we don't have to do anything anymore. It's not there, so it's deleted. And yeah, for that, to get working, we have to inject our informer. We do that via constructor injection here. As you can see, we provided it already in the controller configuration, and also have the imports for it. The next thing we want to do is actually yeah, start creating our desired state based on this request, which is first we want to create our config map in the cluster with that special greeting for the foo. And for that, we first want to define the content of our config map, or at the end, the HTML page we want to display. And for that, we just define a basic example message here. So a headline that says hello, and then it's using the nickname we've specified in our resource. And yeah, we're defining it as with a key index HTML in a config map, so that it can be fetched based on the index HTML key from the config map. And then we are actually in a separate method creating an instance of a config map. And if we have a closer look how that looks like, we can see that, yeah, there is a Java object available for a config map, even if we didn't generate it, because as you know, with that containerized utility, we only generated our foo resource or representation. What the Java Kubernetes client also provides is those Java classes for all types Kubernetes brings out of the box, so config maps, deployments, services, etc. And it also provides builders to construct them to make that in a more fluent way. As you can see, or if you're familiar with Kubernetes, what it actually does is just, yeah, we have to define all yeah, properties, configurations like the API version, then the metadata like the name, the namespace, which we all get from our resource. And what we also do is we define the owner reference. Why are we doing this? Because we don't want to care about the deletion of our resources, like the config map and the deployment, if our foo resource will be deleted. So this is something Kubernetes takes care of if you define those owner references. So the reference will be to our foo, and if we delete our foo, Kubernetes will take care of deleting the deployment and the config map, which is really great. Then we also specify the data, which we created before. So really this config map content, the map of that index HTML and the actual content that will be in the config map. Also to create this owner reference configuration, there's also a builder available that actually provides all the information, or provides methods to put all the information you need for it. You can see, in addition to the name and the API version, etc., and the resource, that's actually the owner, also the UID, which we also have from our cache. Now we have our Kubernetes object representation here with the config map. But at the end, it's like it's not yet available in Kubernetes because we have to apply it to Kubernetes. Actually, what Kubernetes is, so I think you know it mostly from, for example, running kubectl via CLI. At the end, as already mentioned, sometimes it's an API, and we have to send this object to an API. This is also why you saw, for example, in our foo object, that there were a lot of annotations regarding serialization to actually transform our Java representation to JSON to actually send it to the Kubernetes API. And this is what we will do now. For sure, the Kubernetes Java client also provides all the functionality you need for that in a really high abstraction. So let's first add this import and then have a look at what we are actually doing. So we will apply the config in a method here with the configuration, the config map object that we defined. We are also handling some API exceptions. So maybe the API is not reachable, or there's a problem with authentication or something like that. And in this case, what we're currently doing is just like printing out an error and actually triggering the reconciliation of this request again after 10 seconds. So maybe then the API is available and the object, the config map can be applied. Let's have a closer look how we can apply the config map to Kubernetes or to a Kubernetes cluster. And actually, we already saw that for our custom resource, so the foo, we defined a generic API class. And this generic API class really defines the typical abstraction. You know, from Kubernetes, you can create resources, you can delete resources, you can update resources or patch resources. But what the Kubernetes Java client also provides is high abstractions for those resources that are available from Kubernetes out of the box. And this is what we'll use here. And to actually know which API class we have to use, because they are grouped in those API classes, we can run kubectl API resources. And we can see, okay, config maps. So this is, I use grep here that I don't see all, and just the config maps because this is what I'm interested in. We can see that there is no API, it's just a version. The reason is that it's part of the core API. So we will just inject the core API here to actually then apply our config maps. You can see core v1 API is the actual class that provides all the methods we need to apply our config map object. And how we can do that? At the end, it's like there is now not such a method like apply, because as you maybe know, or as I mentioned several times, we are actually using a REST API, and it provides the functionality you know from REST API. So it's like if post, put, delete, patch maybe, and at the end it's like, we don't have an apply method. What actually it will do, the apply, what we have to do is either we will replace it with, which is in the background, a delete and a create, or we will create it. And therefore, because it doesn't provide such an apply functionality here out of the box, our Java representation, we will first check whether the config map exists, as you can see here. So we are listing all the config maps in the namespace, and then we are just filtering whether there's something with the same name available in that namespace. You can also see from the design of the API, it could have been done maybe a little bit better, because you have a lot of options, and it's not really easy readable, because if you don't want to provide them or don't need them, there are no methods available that actually have some defaults, etc. What we do after we know, okay, the config map already exists, we will replace it, which will actually delete it and create it, or we will create it here. So really high-level methods to actually interact with the Kubernetes API for, in this case, the config map. Okay, so after we have the imports, we have more or less everything we need. So if I would run that now with some additional configurations that we need, so providing those APIs, for example, as beans, we would have our config map created. The next thing we want to do is to actually create a deployment. And yeah, it looks for sure relatively similar because we have the same inputs, so name, namespace, and the specification that we maybe need. In this case, not, because the nickname is already set in our config map, so we don't need it for the deployment. So only name and namespace is relevant. And so we first get the deployment in the same way, yeah, creating this yeah, object, so the Kubernetes representation, the Java representation of the Kubernetes object, and then applying it. As you maybe know, a deployment has a lot of configuration options. So it's not only like name, namespace, and then some content. It's a lot more. You have to specify all the containers and a lot more. So there's also a builder available, but it would be a lot of code. And therefore, we are doing creating the deployment here in a different way. What we actually will do is we will create it based on a YAML template. So we just create a YAML template here in the resources. And you can see placeholders like name and namespace, which we'll replace with a basic Spring replacements. And you can also see that, yeah, we have a deployment with 2 replicas, and the pod template includes our Nginx container, so the web server that will actually then serve our website or the HTML page and then display it in the browser. We are defining port, and then also, and that's the important part for the content, we are actually mounting our config map into the container on a specific path where actually Nginx will look for custom HTML pages. So back to our Java code, what do we have to do? We just have to load this resource from the class path. Now we have it as a string. Then we will replace the namespace and the name with the information from our resource. And then there is also from the Java Kubernetes client utility class available that actually does all the mapping from YAML file to the Java class. So in this case, our YAML of the deployment to the deployment class. Okay, so that's really great. Now we have our Java class representation. And the next thing is we have to implement the apply deployment method. For sure, it looks really similar to the config map one. We will also use this higher abstraction that is provided via the specific API class. If we have a look at the under which API deployments are available, we can see that it's the apps API. So we have to also inject the apps API client implementation here, which we'll now use to actually do the same functionality or implement the same functionality as with the config map. So checking where the deployment exists, if yes, run the replace method. So deleting it and creating it, otherwise create it. And last but not least, we have to add the imports. And so that's it really for this easy example of a reconciler. For sure, you can do a lot more complex things. And actually, what it does is that everything is implemented here to based on a request and a specific state you've had from a cache do everything required to go reach a desired state. So, for example, creating pods, etc. But it can be also something outside of Kubernetes. So more and more solutions available, they use just Kubernetes for defining the desired state and using controllers to actually then implement how to go to a desired state, for example, also then on public clouds, etc. We have the reconciler, but as you can see, it's just a class. So you know that we injected reconciler, so we actually also have to provide it as a bean, which we'll do here in our controller configuration. So here's the reconciler, as you can see, and it has as parameters our two APIs, which we'll also provide as a bean here. And so we have to add some imports, and that's it. So now we have our implementation of our first custom Kubernetes controller. And therefore it's now time to run it.
Basically, there's a lot of code there for implementing our 6-line little YAML file for creating a foo. Luckily, we didn't have to write all of it since some of the models were created for us. I'm going to try talking through this stuff a little bit fast since we have 7 minutes left of this session. So basically, in order to be able to run this controller in a Kubernetes cluster, first we need to actually have a container. So instead of creating like Docker files and such, we can use cloud native build packs, which basically it pays attention to what language is your code in, and based on that, it will use build packs and create a container image for you. And since Spring Boot 2.3, it's been something that you can have in there with it. So you can use like Maven or Gradle, for instance, and use the command line to be able to build an image. So basically, we like you can see it there with Maven and with Gradle. And we had done some of this stuff, like basically, if you just run this here, it'll go and actually create it. So we are using Gradle, as you can see. So basically, it'll just run through and you'll be able to recognize some of like the Bell Soft Liberica and different things there for the different build packs that it needs for creating our container image based on all of this Java code that we have so far. So like some of the benefits of having like cloud native build packs is like increased like security and minimized risk. There's also increased developer productivity because you don't have to be like, hey, I need to start with this base image and I need to have these specific CLIs or commands or things I can run in there, and I need to do this and execute this, etc. You don't have to worry about all that stuff. Basically, it's just, do I have here's my code in Java, here's my code in Go, here's my code in one of the other languages. If you just go to, I believe it's like buildpacks.io, you can see a bunch more information based on that. And as you run it multiple times with the same code, if only a few things are changed, there's some level of caching, so that way it'll be faster instead of having to do everything from scratch, which is what is happening this time around. So it ends up taking a little bit longer the first time. But you, again, don't, at least for this, I don't have to worry about what I need to specifically write. It's just, I already wrote the code. Here's Spring, here's my stuff. Please generate this for me. When this ends up finishing, you'll be able to just do a Docker images and be able to see what image that is. And if you're running with just Docker locally, you just have your local image, but Kubernetes needs to be able to pull it from some sort of registry. So we are going to go and push that to a registry. So then basically, we need to add we have a YAML file for our deployment. And so there's specific, using a service count, which is we're using the default one, we need to add a specific cluster role for permissions. So we need it to be able to access the spring.io API group, and it'll show like what resources we get, has specific verbs like, can I do a get, can I do a list, a watch, etc. on those resources. And then you also need a cluster role binding to attach it to the service count, or it doesn't really do anything. And then we also have the deployment that now uses the image that we just created. So we can go and create that with kubectl. And then, so if we do a git on our foos, our config map, and our deployment, we can, if we go and run it again, we can see that we have our foo, and then we can see in a config map we have our my first foo, and in our deployment we have my first foo again. So we have the three things that we ended up, the thing that we created, and the two things that it went and created afterward. The way that we have this system set up right now is we have an ingress controller, so we can just use an expose kubectl expose on our deployment, and then we actually get a link that we can go and use and be able to see our lovely little page, which is just a hello, and then our nickname, which is Spring. And again, this is kind of a lot of code, but it resulted in creating all the resources we wanted and did what we decided that we wanted our controller to do.
Okay, perfect. So now we have our controller running, everything works, but as you maybe know, download applications are really disposable, which means they can be started or stopped really rapidly. And depending on the use case you actually want to implement with your controller, there's maybe a need for really fast startup time to actually scale or deploy, or as said, if there's a problem with the controller, that it can restart really fast. And yeah, if we have a look at our current implementation, you can see that because it's a really basic implementation, our application started in around 2 seconds. And yeah, we can also have a look at actually some resources it used. So we can see one CPU core here and around 150 megabyte. Which means, yeah, so for now it's fine. But if you run a lot of controllers because for the fact that, yeah, they have a lot of stuff to do, it's maybe actually can be a lot. And therefore, the question is there something we can improve that? And yeah, there is something available. As you maybe know, so Spring or Java applications, they are actually compiled to bytecode. This bytecode will be packaged in, for example, jar archive. And yeah, then it will be, this bytecode will be run through an interpreter. And this is really compared to code that will run as a machine language a lot slower. And because of that, there's a just-in-time compiler, which actually compiles some of the code that is, or that is frequently executed to also machine code, which makes the performance a lot better. The problem with that is that it increases the startup time and also reduces more resources, and therefore there's a new way to really focus on that startup or performance in general of the application. And for that, ahead of time compilation is used. So the actual application is compiled to machine code. And this machine code is then executed without a JVM. So important parts of it are then also part of this native image. But actually, this really improves the startup time and also reduces resource consumption. And yeah, so one runtime that supports this is actually GraalVM. And what GraalVM, it has several runtime modes, so it also provides a JVM, but it has this native compilation functionality where we can use to actually build a native image, and also Spring provides this support for it. So from Spring, you can easily compile your application into native images. One problem with that is that actually, because it's ahead of time compiled, it has some limitations regarding dynamic runtime features, like, for example, reflection, etc. And also the class path is fixed. And from a Spring World, also, for example, you're not able to change profiles at runtime. So there are several limitations. I will not have a closer look here because of the time. But actually, if you're interested in this capabilities, have a closer look and what the limitations are, and also how to mitigate them. You can see here regarding the benefits of GraalVM is really this startup performance and the memory footprint. Regarding latency, especially Oracle is doing a lot to improve it also for native images. and also the maturity is getting better and better. But the biggest problem with native compilation is the developer productivity, because the build time really takes a lot of time. So for this easy example here, it will probably take around 10 minutes to consume a lot of memory. For our example, what we have to do to run it through GraalVM and create a native image is we have to add this dependency here. And then we have for both Maven and Gradle support for it. On Gradle, if you added this dependency, you only have to run native compile and it will create you a native image. You have to be aware that it will create it on your current machine architecture, which means if you, for example, like me, on an ARM computer, you're not able to run it on an on-ARM processor. So that's really something you have to keep in mind. But for sure, you can do this then in a CI/CD system. On the Maven side, you have to apply a specific profile that it will be compiled as a native image. And for sure, we also provide cloud-native build packs for that, which is really great. And with that, you can really build your native images within a container on your machine. And yeah, so one more thing we have to do here is we also have to update our dependency for the Java Spring client. So there's also one for ahead of time, which makes this native compiler aware of some of the dynamic features that it's using. And then, because as you know, we also have one custom resource, which is on the class path, one resource that's the YAML for the deployment. So also the native compiler will be not aware of that, and therefore we have to register it. And therefore, Spring provides the runtime hints registrar where you can define all those dynamic features that you're using, like here, for example, with the resource. We have to add the imports and register this runtime hints registrar, and it's important you have to register on a bean. So our reconciler was not a bean or as a bean defined, and therefore we have to do it here. You can see we just reference it here with the import. Last but not least, we also have to make it aware of other classes we are using, so our foo in this case, because of the fact so for most of the stuff, it will be recognized by Spring, but for that, it will be for the foo. So those classes that will be mapped to JSON or something else. So to this object mappers, we have to register them. That can be done by the register reflection for binding thing. Because it takes a lot of time and we don't have any time, so we are also already over time, I think. That's already built for you for this workshop. We will just set the image to the native one. And if we have a look at the logs of the startup time, so as is, maybe remember that before it was 2 seconds, and now we have a startup time from of 30 milliseconds. So a lot of improvement by just compiling the same application to a native image. And you can also see the if the application is available in the metrics, so it takes some seconds, you can see that the memory is reduced a lot from 150 megabytes to 29, and usually you can also see some CPU reduction. One last hint here is that there's also a new functionality that will be integrated in Spring Framework 6.1. It's JVM checkpoint restore. So it's another technology trying to achieve the same. So fast startup times. What it does, it's making a snapshot of the running application. And then the application is able to restore from that. So also other instances that are running in parallel if you store the checkpoint somewhere, maybe in the container image or also on persistent volume or something like that. And yeah, so that's it for our workshop. And I hope you enjoyed it. Here's also a QR code with a sample code if you want to have a closer look. And yeah, thank you very much.
Thanks, everyone.